Folks, good noon.
Good noon.
All right, before we get into crypto, I wanted to make some comments. I was going to send out an email about this, but I'll tell you all here now since you're here and probably announce on the mailing list. I read through some of the submissions for part 2 and 3 for the homework. Some of them are very good, some of them are not so good. And the reason why the ones that are not so good is because they are neglecting the English part of the writing assignment. So remember we said the goal is to actually write something that is reasonable and easy to understand, as if you were writing a report or a letter to your boss or something, right? So some of the things I've seen, like a series of just like one sentence bullet points, are not appropriate for this type of communication, right? So the idea is to get you thinking in terms of writing paragraphs that have sentences that logically follow each other, right? So part of, and I'll make this more clear in the mailing list, but I mean, part of the assessment of those parts is not just the technical content of the answer, but also your spelling mistakes, grammar mistakes. Are your thoughts clear and logical? Are your sentences follow each other? Are your paragraphs properly structured into something that makes sense? So, and if you submit already, you have time to change that. So that's good. Any questions on that? Yeah.
I have a question on
Sure.
part 4. Are the user names unique, or can you have multiple users?
Let's say yes, they are unique. So they would be like, since we're not doing any authentication in this, you'd see that the name is the identity.
So you can have 2 users with the same name?
They would not be 2 users, they would be 1 user. Yes.
And can the keys be used by multiple people? So 1 key could be used for 2 users?
What does the policy say?
Only users with authorized keys.
So how would you take that to mean?
If you have the key, then you cannot change it out.
Yes.
I know that the events are case sensitive. In the test cases, for when you do a command like insert key, is it still going to be in all caps like in the description?
It'll be, yes, the test cases exactly follow the policy in the homework description. So if it says it will be in this form, then it will be in that form. If it says that your output needs to be in this form, then your output will be in that form. Yeah?
For part like 2 and 3, is there like an upper limit of like how much you want people to write? Like I don't know if you want to like read an essay or anything.
I mean, how long are we talking? Like 12-page paper?
No.
If you write something really long, I will read it, but it better be very good by the time I get to the end. Like I said, it's more about comprehensive. So if you feel like you need to take time to comprehensively answer the question, I think that's absolutely a good thing. Yeah, so no hard upper limits. I don't want to have to set like a file size limit on ASCII text being uploaded. Cool. All right, let's get into breaking crypto, or crypto. We're talking about crypto systems, and we modeled, just as a kind of a refresher since we already covered this stuff on Thursday. A crypto system we talked about basically has, we can think of as having 5 elements. What are the elements of our crypto system? What do we need? Yeah, in the back. An encryption system, so what does it do? What is the encryption system? What does it take in? It takes in a plain text and what else? A key. We need a key. We need some kind of key, right? So we can think of it as an encryption system. So E is basically our functions that take in a plain text and a message and a key and output ciphertext. And so already basically implicit in there, kind of in this formalism, M is a set of plain text, K is a set of all the possible keys, C is the set of all ciphertext, and an encryption function maps a message and a key into some ciphertext. And so then a decryption function does what? what sense? So what does it do here?
So the input for the decryption system is the ciphertext and the key.
Ciphertext and the key?
The output is plain text.
Output is plaintext, perfect. Cool. And so for the security, well, we'll talk about that actually in a second. So we talked about a Caeser cipher, so that a Caeser cipher actually was used by Julius Caesar, which I think is kind of cool that we still talk about it and it's still relevant. And so we talked about there, a Caeser cipher is, the messages is a sequence of letters. The key is some integer from 0 to 25 that tells us how much to shift all the letters of the alphabet. And so the encryption is pretty simple. The encryption is take the letter, for each letter of the message, for every letter, shift that letter k number of characters forward, and the mod 26 is so that we'll wrap around. And so if we're shifting by 1, Z will move to A. If we're shifting by 2, Z will move to B. Anybody have questions on this? Seems pretty straightforward. Yep.
Maybe a little off topic. Is that
Sorry.
what the Turing did?
I think you're talking about the Enigma machine,
Yeah.
like the German Enigma machine that Turing helped break.
Because it's
To
really
be
different every day.
honest, I don't know. I'd have to look into it. It probably is not this simple because that would be very easy to break. But as we'll see, all crypto systems have some kind of combination of these types of things, of substitution and rearrangement. So it probably did something like that. That'll be interesting. Maybe a good homework assignment.
Sorry.
No, you're already going to do that. You will be breaking some crypto, but it would be cool if it was like the Enigma machine or something. Okay. Cool. Oh, maybe we can watch the movie in class. All right. That's a bad idea. And so decryption is very simple. So if you know the key, you can decrypt the message by taking every letter in the message, subtracting from the key, that letter, and that will reveal all of the plain text. So the important things here is that ciphertext and message, they're both the same language, right? I mean, they're just letters. We're not, and this is, I would say, true for most crypto systems. You don't want to assume you have some crazy language that's not exactly the same. So even when we get to more real crypto systems, they operate on bits, right? Zeros and ones. So cool. Any questions here? So how do we break a crypto? So when we think of crypto, we want to think in terms of adversaries. So the adversary is the person who wants to break the crypto system. So why might they want to do that? What's the motivation behind our adversaries here?
Read our messages.
What's that?
Read our messages.
Read a message. Why would you want to do that?
To win a war.
To win a war? Yeah, so a large part of, if you know where people are or where they're going to be, you can plan accordingly. Yeah, that's definitely, what else? Leak information, what kind of information? Personal information, so maybe you want to read, I don't know if this is a true statement, I'm pretty sure. I think all my tax returns are on this computer in my Dropbox, but they're all encrypted. So if somebody broke into my Dropbox, they should not be able to read those files, right, of my tax returns, because they're encrypted. So if they can, that would definitely be a problem. I should verify that that's the case after this class. I just reminded of that. What else? No other motivations to break this?
Just for the thrill.
For the thrill? Yeah, that's true. Yeah, in the back?
Well, if you break it, then you can also send your own messages.
So if we break it, maybe we can inject our own fake messages into there and cause chaos and confusion. That's a great point. I hadn't actually thought about that. What else? I think you had your hand up. Somebody over here. Yeah.
To expose security flaws.
To expose security flaws? Yeah, so maybe we don't actually we're not an adversary in the sense that we will cause harm by breaking this, but maybe we are cryptographers who want to demonstrate that a known crypto system has flaws, right, that can be taken advantage of. And so, what should we assume about our adversaries? So when we're designing a crypto system or we're discussing a crypto system, we need to think through, well, not only what's the motivation of the adversary, but I think there's a lot of reasons why they would want to break the system, but what do we assume about them? Yeah?
I think it's safe to assume that they'll use any means necessary.
They'll use any means necessary. Why is that safe to assume? And what do you mean by safe?
Well, if they're trying to break your cryptography,
Mhm.
they're obviously doing something you don't want them to do. So your feelings are not important to them. And I mean,
Depends, maybe they're your allies, but.
you know, probably the law is not important to them either.
Mhm.
So whatever they're going to do, they're going to do it.
Okay, good. Okay.
Safe. Explain the safe part.
Yeah, what do you mean by, or does somebody else want to define safe? You can do it. Let's go there.
Like no possible way for them to get in. You want to close every way of attacking it and breaching your system. You don't want there to be some kind of vulnerabilities.
Right, so I guess the question is, do we assume that this person is a, I don't know, I'm trying to think of a good person who's not skilled, but also not like, I don't know, like a 10-year-old who doesn't have a lot of math background, right? Who could become an advanced cryptographer, but is not quite yet. If you assume that that's who your adversary is, then why not just use a Caeser cipher? Like, I don't think a 10-year-old could be able to break that, or it may take them a long time. I don't know. Right, so by safe, we're kind of assuming a very powerful and strong adversary in that sense, right? So so going back to this, what should we assume that the attacker knows? What's that? In general, but about a specific system. So when we're talking about the Caeser cipher, and we're thinking about, okay, somebody wants to break this, what do they know?
The alphabet.
They know the alphabet, so they probably know the language, the set of plain text and the set of ciphertext, right? Yeah.
They probably know that what they're looking at is encrypted.
They will probably know that they are looking at something encrypted. Yeah, we'll get into stenography and other types of stuff like message hiding things later, but that's definitely, I think, a safe assumption. Yeah.
Again, just drawing on from some of the other classes you've been doing, I think it might be safe to say that they know our encryption function. If we're using a good one, the best ones out there are, the function for it's known, right?
Yeah. So I don't know. What does everyone think? Should we assume that the attacker knows at least E, the function that we're using? Is that too strong of an assumption? Yeah.
I don't think so. I think that if I was setting up encryption, I would assume that whoever I'm dealing with knows at least everything that I know about encryption. You know, and so the only information that I can keep hidden from them is literally keys that are, protected by, by just hiding them.
So going back to the safe assumption, right? If we want to assume a strong adversary, we should assume, I can't remember who said the encryption algorithm, but we should assume that they know E, the encryption algorithm, and D, right? I mean, we'd assume if you know the encryption algorithm, you would know how to decrypt it. But the important piece of information so I guess the other question is, should we assume that the adversary knows the key? Probably not, because then what are we hiding from them, right? I mean, if they have the key, they know the encryption system, they have the ciphered messages, they could not only manufacture new messages, they could easily decrypt everything, right? So the key literally is the key to all of this, right? So, yeah.
But at the same time, there's a lot of encryption methods, so just because they know all the possibilities doesn't mean they understand exactly who you're using.
True. Although the flip side then is whoever you're communicating the message to has to somehow know what algorithm you're a lot of the modern crypto will actually say in the metadata of the message exactly what algorithm is being used. So yeah, it's an interesting thing because you think, well, if I have to keep the keys safe, then I should just keep the algorithm safe as well. But so there is a little bit of difficulty there, but you have to keep something secure, and in this case, it's the keys. And so the idea is, and you have a lot of benefits by the algorithms being known in that other people can attempt to find problems in these algorithms, right? People who are a lot smarter than you, hopefully, and be able to break these crypto systems. So it's a good discussion. Because it does inform how we think about crypto systems. So we assume pretty much always that the adversary knows the algorithm but not the key. So, but is the, let's say, I guess another way to maybe think about this is if I create my own crypto system and I, let's say, just use it to write messages to myself or to store my own data. Is that a secure crypto system? Is it a good system? I'm saying not only do I have the key, but I also have the algorithm. You're shaking your head, why not?
Depends. If you use the Caeser cipher and you're storing paragraph, text information, then you can look at statistically analyze what the output is and statistically reverse it without ever knowing what the algorithm is because you're not doing something that obfuscates.
Right. Yeah, so I think the key, well, kind of the key idea here is the opposite of this necessarily isn't true, that hiding the algorithm means that the system is necessarily secure, right? Because, and this actually comes up a lot when you talk about real world cryptography and companies who actually use crypto. And what they'll do is they'll say something like, hey, here's $1,000 to anyone who can break this crypto system. And they have this contest for like months. And after 6 months, they go, nobody has broken our crypto system. That means we're definitely secure, right? And it's like, well, not really, because A, $1,000 is not that much of a cryptographer's time, of what a cryptographer would be doing to analyze this. And just because nobody's broken it publicly doesn't mean that it's not broken. And so this is kind of an important thing to keep in mind, is that keeping the encryption algorithm secret or claiming that nobody's broken it is not necessarily a proof of security. So, what should we, so we kind of assumed, so we assume that the adversary knows the algorithm used, doesn't know the keys. What other possible capabilities could an adversary have on our system? Like, what can they do? I mean, think about different scenarios like we just talked about, right? Like, in a war environment, in a file on my computer, yeah.
They can deny us access to the system itself.
Yes, but then they're not actually breaking the crypto, right? If they're denying us access to the system, because presumably I can stand up a new system, assuming I can safely transfer a key from one place to the other. Yeah?
So they can collect different ciphertexts, and depending on what type of algorithm it is, they can just try and guess the key until they get something that works.
Right, so one capability we can maybe say is and let's restrict it even more and say they only have access to the ciphertext. Right, so they only have, like, let's say, thinking about maybe a war scenarios, you've intercepted some message or some communication. Right, you know the algorithm being used, but you definitely don't know the key, and maybe this is the only message you have. Maybe you have multiple messages, but you may not know if they were encrypted with the same key or not. That may be something that is difficult. So is this it? Are there any other capabilities that an attacker can have? I would say this is kind of, when you think about the adversary's capabilities, this would be on the bottom. So this is kind of at the very least, you want some ciphertext to work with. But yeah.
Can we assume they have comparable systems to what we have?
Yes, you would assume they not only have comparable systems, and this kind of comes in assuming a strong adversary, right? So you assume, well, And it does depend on your threat modeling, right? You may not assume for a company that's a nation state may necessarily want to try to break your encryption, where if you are a nation state, you would assume that other people have your capabilities, or maybe even better, so that you would try to design that in. Yeah?
You could have the plain text and the ciphertext that's associated with it.
Yeah, so I may, through other means, maybe it's an incredibly simple message, maybe somehow I'm able to figure out the plain text. So I have one instance of a message and a ciphertext, right? And the question is, can I derive the key from that in case that key was used in other messages, or like we said, to encrypt our own message? So this would be intercepting maybe, or, well, I guess I don't want to go too far down that route, but like you could interrogation or use other means to like get a copy of the message and the ciphertext. Do you control that message? In this case? What was that?
I don't think so.
No, because it's
Because your adversary has it.
your adversary created that message, and you have the associated ciphertext with that message. So then, what if that's not the case? So kind of the next level up would be if we, the adversary, can choose the plain text that they want encrypted by the system. So here not only do you have a message and a ciphertext, but usually you can make frequent queries to the system to get additional messages encrypted of your own choosing. And so this is basically kind of reversed in increasing sophistication and capabilities of the attacker, where, as we'll see. Yeah?
Possibly get one of the keys, like for instance, like say that they get an account and then they get the key for themselves. From that, could they possibly say, well, we got this key, and now we have an idea of what the keys look like?
Usually, you would say that if they break your key, it's game over, right? So if they get access to your key, it's essentially done, and your system is broken. It may not have necessarily a cryptographic weakness, right? It may not be something to do with the algorithm itself. It's the fact that you lost the key, right? So you can have, and actually I think most crypto systems are, like modern ones, are resistant to even chosen plain text attacks. So even if you encrypt whatever you want, that doesn't mean that you can derive the key from just the chosen message and a ciphertext. But if you leak the key, then it's done. Everything's over. So you can now do anything you want. But you haven't broken that specific algorithm or that crypto system. You've broken that implementation with that key. But if they rekey and do a new system or something, then you'd be good. Cool. So most attacks on crypto systems come down to a couple broad categories. So one is really like a mathematical attack, where there is some mathematical flaw in the algorithm itself, and somebody finds that and is able to derive some kind of attack. What are other types of flaws? Yeah?
Couldn't you have a flaw in how it's coded? If somebody has like a bug in it, they could exploit it?
Yep. So there could be, the algorithm itself may be secure, but the implementation has flaws in it. Maybe if they need high quality random numbers, but they're pulling from not high quality random numbers, that could cause an attack. And that's not necessarily the mathematics. The mathematics of the crypto system is fine, but the way that random numbers are generated are not. This actually came up, I believe, I should probably verify this, but it's a good story, is that there used to be, I think, online poker games that would, there was an online poker system that would randomize the deck based on a random number that turns out was generated based on time, like just the Unix timestamp. And so people figured this out, and so they realized they could very quickly guess, you could guess a range of a minute or something of what, because you don't know exactly the time on the server, but you can guess. And if all it is second-based distinction, you could then play out those games, and then figure out where the cards are going and what cards you have. That would winnow down to exactly what all the cards everybody has, and at that point you basically broken the game. So yeah, but that's not necessarily, randomly shuffling a deck is not something that's inherently insecure, but how you choose that random number is. Cool. What else? What are their attacks?
Key exchange.
Yeah, what's that?
Key exchange. How the keys, depending on the system, how the keys are transferred from party A to party B.
I'd say that's outside the scope. But it is something definitely, we will talk about that, especially when we get to asymmetric cryptography. We'll talk about why that's better, and it comes down to this exact issue. Because there is this problem with, if I want to talk to any of you, we have to find some secure way to exchange keys, right? So we can talk to each other. But how do we actually do that if the whole reason why we're using encryption to communicate is because we believe our communications are being monitored, right? So how can we then safely exchange keys? It's a difficult problem, but we'll ignore that for now. So what else?
Side channel attacks.
Ooh, in what sense?
Even if the algorithm that you implemented is good, there could be flaws in the hardware that it's implemented on.
Interesting. Yeah, let's file that under implementation problems, because that's another, it's actually used to be a big problem with crypto systems, is you would, based on the timing, so if you can choose your plain text based on the time it took to encrypt that, it would leak information about the keys. And so they've had to develop entirely new ways of programming with constant time programming. So no matter what input you give it, no matter what the key is, the input, it always takes a fixed amount of time to execute. What else? You had an idea earlier.
Side channel was what I was actually thinking.
When we talked about looking at my file on with my crypto system, how would you break that? Yeah.
Statistical analysis.
Yes. So what does that mean?
So
Just throw statistics and deep learning at it?
based on the probability, or based on how often certain letters are used in language, we can compare that to encrypted text. Try to.
Yeah. So we know English text. English is not random, right? Some characters are used more frequently than other characters. Anybody know what's the most frequently used character? E. Yeah, so there's a whole thing. You can analyze text to figure this out. It is not a random distribution, so you could analyze just the ciphertext itself to see if these same properties maybe hold, or maybe there's some information in the ciphertext that is left after the decryption process. So there's basically a whole category of attacks on this of trying to statistically analyze the ciphertext. If you think it's just kind of the simple ciphers we'll talk about because we can do them by hand, it's actually not. So I believe, I can't remember, was it DES? One of the first major big kind of encryption algorithms that was standardized, they found out had some kind of statistical attack that it was still leaking information based on the encryption here. So this happens in real systems. It's not just these kind of more simplified ciphers. And so we talk about implementation flaws, right? So the important difference between these is mathematical attacks is basically the core mathematics is wrong. Statistical attacks means math is fine, but the information that is left from the message or the key in the ciphertext is still there. And so the encryption algorithm is not properly hiding that. And so therefore we can try to make some assumptions and break it that way. Whereas implementation is all of these two can be fine, but there's a problem in the way that it's actually implemented. So we're first going to look at classical cryptography, as it's called, or symmetric cryptography. The idea is the sender and receiver of this message both share a common key. like we said, if it's just me, that's pretty easy, right? I have a password, that could be the key, it's in my brain, nobody else knows it, right? Whereas when we have to talk, we have to somehow exchange this key in an out-of-band manner where we both actually trust. An important kind of distinction here is the keys don't have to be exactly the same, right? They could be slightly different, but if we say, I don't know, if it's any way trivial to derive one key from the other, it basically falls under classical cryptography. That doesn't work. Yeah. So symmetric, so where does symmetric come from here?
Both the sender and receiver are using the same key.
Exactly. The keys, right? We think we both have the same key, sender and receiver. And there's two basic types that we're going to talk about, and this is actually true for simple ciphers and also true for incredibly complicated modern class crypto systems. Substitution ciphers, which the Caeser cipher is the first example that we'll look at. So based on the key, you substitute one character of the message for some other character. And the other way is move characters around. So you could make an encryption algorithm that says, for every 2 characters, swap them. Right? So that would be a transposition cipher. And yeah, modern crypto systems, modern classical symmetric cryptography is a combination of these things. So you do a series of substitutions and a series of transpositions, and you do it kind of over and over. Cool. So we already saw this with the Caeser cipher. So with this substitution cipher, sorry. So the idea is if we have a Caeser cipher with the message hello world, and we want to use, let's say, a key of 3, what would the ciphertext then be? Yeah, every letter shifted 3 to the right. So X would go to A, Y would go to B, Z would go to C, and so on and so forth. So the key would be written, you either write the key as 3 or the letter D. So this would be kind of how it's often written in these types of crypto systems. So the ciphertext here would be cool Zerg. So how do we break this? So is there any problem with the math necessarily? Yeah.
There's no real problem with the math, but
there's not a lot of math.
Yeah, it's more so with the implementation because you only have 26 possibilities that you can shift it by.
Okay, true, but I wouldn't say that's tricky. Yeah, I guess it does depend on how you define the crypto system and how you define keys and everything, right? So one flaw would be that we can only send messages with no punctuation, right? Only letters. So maybe we want uppercase and lowercase letters, maybe we want spaces, maybe we explicitly don't though. So that could be a problem. Right? So how do we want to attack it? So Will says we should just brute force it. Right? Which actually, so if you're, I don't think I mentioned this here, but when you are interviewing for a programming job, this should be your first idea for everything, right? It's like, how do we do this thing? I don't know, just brute force it, try all possible combinations, right? If only to buy yourself more time to think about a good answer, but it also shows that sometimes brute forcing it is correct, is the right thing to do, right? If you know you only have 10 elements, then do whatever kind of sort you want. Do a bubble sort. It really doesn't matter at that point. As long as you know that it's correct and your brute force is actually correct. Actually, I guess I can talk about this. Yeah, so this last weekend, we were playing in a CTF, and there was a challenge that was looking for, it took a string and called Java's hash code function on it, And this string that it gave you had special characters in it, like a $sign, but the actual, but the input to the function could only be alphanumeric, so you couldn't actually use this $sign. And it would check that the hash code of the string you input was the same as the hash code of the other string, right? And so I looked into the math. You can look at exactly how Java calculates hash code, and it's this formula. And it was kind of late, and I don't know, I'm not really mathematically oriented, so I was like, I can't figure out how to make the math work right, so I just said, screw it, I'll just write a brute forcer. And so I wrote a brute forcer and left it running overnight, and when I woke up, it like found the answer. And part of that is because it's actually super quick for Java to do these hash code calculations. So you just do this in a loop, try all possible values, and at some point you'll eventually hit it. So that was fun. Yeah, so you can completely, oftentimes, especially as hardware, and this was just on my laptop. I mean, I wasn't using like a 20-core machine or anything like that. But yeah, sometimes it's just worth it to do a back of the envelope calculation, like, could I actually brute force that? And in this case, we only have 26 choices, right? So you can just do that and look at all of them and say what actually makes sense to me. So that should definitely be kind of your first idea and your first approach to a lot of these things. We'll see that quickly falls away the more combinations that there are. So then, what should we try? So let's say it is maybe not feasible.
Look for patterns.
Look for patterns. What kind of patterns do you want to look for?
Double L, or look for small words like A.
Ah, okay. So yeah, so let's go back to our ciphertext here, right? So, so the idea is here we could maybe do an analysis and figure out how many let's say English two-letter words are the same, like letters right after each other that appear. What are the most common? And so you'd say, okay, if I have a zero, if I have an OO, that probably could be either an LL, or actually I don't know off the top of my head what common two-letter words are in English. But you could try those and derive a key from that, and then try these values to prioritize what of the 26 you're going to actually try. Cool. What else? You had a same thought. What was that?
Rainbow tables.
What's a rainbow table?
Basically, you have a lot of common information and their ciphertext, and you can see, you can run them all through to see if anything, like the ciphertext that you're looking at, matches anything in your table.
Okay, so we haven't talked about rainbow tables yet, but yeah, that's a good point. So you can basically pre-compute. So kind of going, the idea is basically pre-compute. So the idea would be take the top 10,000 English words, right, and encrypt all of them with all the possible keys, and then see which of those appear in the ciphertext more often. So you'd probably be able to find it that way. That's a good one. As the number of keys increases, though, that becomes less and less feasible, right? Because you can't, as the key size gets larger, your table then has to be much, much larger. With a hand in the back. It's, yeah. So we can also just do an analysis of, so we can do some kind of statistical analysis, right? So we just talked about that English has a different distribution of letters, right? So the letter E is a lot more frequent than the letter Z, right? The fact that we have a Z in here pretty much tells us fairly well that we are not in the correct language here. But, so how does so if we peek ahead for a second, and we take this nice graph from Wikipedia, and this is the graph of English character frequencies. How does this graph change by the Caeser cipher? So I think we can all agree our input language, our message, will follow this graph, and the more characters we have, the more true that will be. So what does the Caeser cipher do this? Yeah?
It should just shift everything, however, whatever your key value is.
Right, so and the important thing to remember is our message is not going to be exactly this, right? Our message, for whatever reason, let's say we have code words that start with Z a lot, right? So there happens to be more Z's in the message. But the important thing is whatever the distribution is of the original message, the ciphertext is only going to be that shifted, right? So that leads us to basically, so we talked about already, we skipped ahead to a two gram model of English. So this is basically 1 gram, so just looking at letters, so not a letter and what follows it, but just looking at a single letter. And so if we have some ciphertext that we'll talk about, so I guess let's talk about this. So how would we, let's say you're just given this ciphertext, like we say, let's say we assume the adversary knows how it's being encrypted, but let's say we don't. How would we maybe check? Or what would we, I mean, obviously if you can break it using a Caeser cipher, then yes, it's encrypted with the Caeser cipher, but without necessarily breaking it.
Well, you could start just by seeing which letter is used the most, assume that that's going to be the most common letter in the alphabet, and then just kind of work your way down. And
yeah, you could see if, exactly, sorry. You could basically take, let's say this graph, there's another graph that I don't have, but it's on the web. If you just Wikipedia letter frequencies, that's where this graph is. You can sort this by most to least frequent character, right? So you're gonna have a distribution like this. You can do the same thing to the ciphertext and see that yes, it roughly follows that same distribution, right? If it's flat all the way across, what does that probably mean?
you're screwed.
Not yet, but it's probably not a Caeser cipher because that would mean that every character is used equally, which would probably indicate if every character is used 1/26th of the time, that would probably indicate that it's random, right? That it's just, that the ciphertext itself is at least random. But remember that only is looking at 1 gram frequencies, so there may be other signals we can use. Cool, so what we can do, so we can compute the frequency of each letter in the ciphertext. You can do this by hand. I highly recommend not doing it by hand. It's a lot better if you write, and this is why things like Python's great for this actually. I use IPython when I'm doing stuff like this, so if you haven't played around, if you know Python but you haven't played around with IPython, it's like a better Python, like when you just type in Python and you can write code. So IPython has history and searches, and it's really awesome. So I highly recommend that. So we can take this, we now have the frequency of each letter in our ciphertext, and so what's the most frequent letter here? Was it B?
B.
Yeah, B. So it's probably not, that's not really the English model, right? So that's probably not where we want to be. And so we can actually perform an analysis here, and the idea is calculate the correlation of the frequency of the letter in the ciphertext versus the frequency of a letter in English. So you can compute, and it's really simple. So if we say that px is the frequency of some character x in English, and f of c is the frequency of the character in the ciphertext. So these are very easy to compute. You just literally count the occurrences of a character divided by the length of the string. That is the frequency of the character. Where would you get px? From where? A table from where? Yeah, anywhere. Wikipedia. I mean, there's crypto book. There's probably one in our book. There's tons of these. How would you actually derive that table if you needed to derive it? What was that?
Take a few documents and index them that are in English and count the numbers.
A few. What if I take documents that are specific to, let's say, computer science?
It may not have the same frequency.
It may not have the same frequency.
You need large numbers, large enough numbers that the statistics work out more consistent.
Right.
Probably dictionary.
Dictionary, so you could use a dictionary, right? What would be the problem with using a dictionary though? Exactly, so a dictionary would be great because it would give you the frequency distribution of the letters in all of the words in English, but it doesn't take into account the fact that the will be used a lot in English letters, so TH and E should be used more frequently, right? So where can we get that from? Where do we get these documents from? Yeah.
Well, wouldn't it be, if you were going to compile one on your own, would it be useful to actually take a subset of documents relating to the topic that you're working with?
Sure.
So like, you know, if it was war, like you would just want to grab a whole bunch of war documents.
Yeah.
And that would give you a way better estimate than taking like newspapers and People magazine and a whole bunch of essays by school children.
And if you have known messages, then that could actually feed back. If you know the messages, even if you don't actually know the ciphertext, if you know what some of the messages are being sent, that could definitely inform that. Let's say you want, how are these tables generated? I mean, literally, how would you do this? You live in an age where all of this stuff is available and you could go calculate these tables. Nobody needs to pre-calculate these tables for you. So how would you do it? Web scraping, so you can crawl the web.
URLs and
there's even, I don't remember the name of the project, but there are some projects that will already have crawled the web, and they have terabytes of data on all of the things there. That's a little tricky because you need to scrape out all of the HTML, so you need to make sure you're only extracting the text, but you could use something like Beautiful Soup or something to do that. What else? How else would you do it?
Public books.
Public books? What are those?
Books that are no longer copyrighted and available.
I think that's Project Gutenberg, I want to say. So there's publicly available text of English books, and that will be biased a bit because it will include a lot of old stuff, but you could actually download probably tens of thousands of books and analyze those. You could download Wikipedia itself and use the English Wikipedia as input to this system and do this, right? So, yeah, like we said, of course, if you're then targeting a specific system or a specific group, you would definitely want to include those things more often. So yeah, that would be cool. But yeah, the point is that like you can create all of this. It's not just, you don't have to have it be given to you. And so the correlation is incredibly simple. So the idea is you're trying to calculate for a given I, so this would be the key. So for each key, go through every character in the alphabet, calculate the frequency that that character occurs in the ciphertext, multiply that with the frequency of what that shifted character would appear in English, and add that all up. And so the idea is this will give you a pretty good measure for each of the keys. So you can actually calculate this for our previous ciphertext, which was, where was that? Here. For this ciphertext, so we can see, and this I've sorted by the correlation. So we can see that 23, 13, and 7 both have a fairly high correlation. Does this guarantee that the one on top is definitely the one? Not necessarily, right? I mean, our ciphertext is pretty small in this case, right? Our ciphertext is, I don't know, 20 letters or something like that. I don't know exactly what it is, but I don't want to count each letter. But our ciphertext is not incredibly large, so we'd expect maybe some characters are kind of offset. And then we just try each of these kind of in order and see if they make sense, right? So we could say, we could try 23. Does this look like the ciphertext? No. Yeah, no. It's always difficult to me when they don't have spaces in the words, because I keep trying to make words that don't exist. So we try 13. Does this look like something? Yes. You should never build your own crypto. It's true. And we can try 7 just to see that it kind of, but we can see there's actually a lot of E's. There's E, 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 E. So maybe according to the distribution, this is this is more likely. But just because of the words, there's only what, 1, 2, 3, 4, 5, 6, 7 words, right? But still, that's what's kind of crazy is that even those 7 words still follow the basic distribution. So using this, you can figure that out. Questions on how to approach this? So what are the problems with the Caeser cipher?
Easy to brute force.
What was that?
Easy to brute force.
Easy to brute force, only 26 characters. What else?
Oh, yeah, that's what I was gonna say, is the key space is small.
Key space is small. Is that it? So another way, oh sorry, yeah, go ahead.
Doesn't mask the statistical occurrence of letters.
Yeah, it doesn't matter. As we just, I mean, this is literally how we broke this, right? Is we looked at the statistical analysis of the frequencies, right? You could see that it's just shifting the frequencies one way or the other. It's not necessarily completely hiding the distribution of characters. Yeah.
I guess this is a weakness compared to some more modern algorithms that if you re-cipher your plain text like 100 times, it doesn't do anything. So like if you shift all the characters left by 23 and then you shift them right by 12 and then left by 5 and then right by 27 and then left by 100, if you did that 100,000 times, we could on that string do the same analysis you just did and pick our top 4 choices. And again, that's mostly because the key space is small, but also it just doesn't change anything when you re-cipher your ciphertext.
Right, and so, yeah, so we actually just, that's a good point. So it doesn't, like, let's say compose, it doesn't necessarily give you anything, although we'll probably touch on a bit, even modern crypto systems, people are wary about feeding it back into itself mainly because it's not really analyzed to do that, and so people don't really know what to make of that, right? But you brought up something else that now I've got. Crypto systems. Multiple encryptions. Okay, well, they'll come back to me. So definitely the key is too short, right? We can just search. Statistical frequencies are not concealed very well. The repeating part. So let's say we have like the word hello or the repeated multiple times throughout the ciphertext, right? That will still appear, those 3 letters will appear in the, if that appears in the message, those 3 letters will appear in the ciphertext over and over again. And, as an adversary, so we broke this with a just ciphertext, right? We didn't actually know the content of the message. But if we knew the content of the message and had the ciphertext, would we be able to get the key? So like a plain text attack. Yeah, we would be able to get it incredibly easy. And what about if we could choose the plain text? How would you do it? What would you choose to encrypt?
One character.
What character?
Any character.
I would do A, right? A would be the easiest. That would tell you exactly what the key is, right? You literally just have a message of A, and it will decrypt, encrypt it to whatever 13 is in this case, and then that's your key from there on out, right? So it's incredibly, it can be very, very mildly resistant to a ciphertext only attack if somebody does not know how to do this, but yeah, it's all of these problems. So, but it's pretty good, for like Roman times, this is pretty good, it's pretty sophisticated. I was actually reading something that was like, it was really good because a lot of people couldn't read, right? And there were a lot of languages anyways, and so if you saw it, you would just assume it's a different language. You wouldn't assume that it was something enciphered or encrypted. You would just assume it was some other language that you've never heard of, and just ignore it, so, yeah.
It's too bad the masses aren't totally ignorant these days.
It's not necessarily a good or bad thing. So, how would you improve upon this algorithm, this crypto system, while still keeping kind of the same substitution style? Yes?
Something I did in a previous class is we took the key to encrypt the first N letters of the message and then started using the message to like kind of shift over the resulting
Yes, we'll get to that in itself. You could kind of basically use the key to encrypt the message, and then use that part of the message essentially as kind of the key to encrypt the next part of the message, and you kind of feed the encrypted message back in on itself. But we'll get to that. Yeah.
Use a frame, so using the same kind of methodology, but you put a message over a message. So it'd be like you use like a short phrase, like "All hail the king" or "God save the queen" or something like that, and then put that over repeating of it, and you ship the letters by that phrase every single time.
Yeah, so the key idea there is just make the key longer, right? Part of the problem here is the key was one letter, which was 26 characters, which meant that there are only 26 possibilities you had to search for. So an idea here is to let's use multiple letters in a key. So let's get a key, but let's have multiple letters. We'll actually talk about what happens when the key is as long as the message, so that's something else. But the idea is to really try to smooth out the statistical frequencies of the letters in order to make this harder. So anybody speak French and can pronounce this name? Vigenère? Shoot, I will never get that. Vigenère? I have to practice this at home. So this person came up with this cipher. The idea was actually what we just talked about. So similar idea, but use a phrase. So that if the message was, "The boy has the ball," which I don't know why that would be your message, but it's a really good example. We'll choose in this case so actually we can touch on this in a second. So if my key was, what's this, 12 characters. So my key was 12 characters long, right? And was, let's say, pretty randomly created as a key. That would basically hide completely the statistics of the underlying language, right? Everybody agree with that? So if every single letter is encrypted randomly, each letter is going to come out as something random. Right? But what's the problem there? Yeah.
Seems like if you knew somebody was using a cipher and it like leveled out, you could get the letters in the cipher by the way that they level out the frequency.
But let's say that in general, let's say I have a message of size n. I just create a key of size n and choose the key randomly and then encrypt it. So that way each letter is essentially randomly changed to something else. Yeah?
The problem is that the key has to be as big as the text, so the key would be really, really large.
And I have to give that key to you somehow securely. So if I'm giving you a key of the length of the message, why wouldn't I just tell you the message if I can do that securely? So yeah, we'll touch on this later, but I wanted to kind of just mention that a little bit, right? Because exactly that point, right? The keys are just as long, and then you have the problem of reusing the key. If you reuse the key, you could leak information. So let's use the key VIG. So this would be the key. So how many possible combinations are there that you would have to search for if you knew that it was, let's say, a 3-letter key?
The amount of
17,000.
So how'd you derive that?
26 to the 30.
Yeah, so each key could be 26, so 26 times 26 times 26, right? There's 26 possibilities for the first one, 26 possibilities for the second letter, and 26 possibilities for the third. It's 26 to the third, which is about 17,000. That's still not impossible, right? I mean, you could presumably, if like I was paying you a lot of money, or you're in the military and you had to, you could go through, you could write a computer program to print out all possible 17,000, ciphertexts and see which one looks like English. You could write a program like we talked about to maybe do statistical frequency to figure out which one of those was actually correct. So you could definitely do this. But the idea of how this works is you take the key, you repeat the key, right? So the idea is the first character of the plain text will be encrypted with V. The fourth character will also be encrypted with V, right? And the second character will be encrypted with I. Sorry, I say encrypted, like Caeser cipher shifted, right? So with I, and G would be the third character. So you get something like OPK, WW, whatever, whatever. And importantly, right, compared to our previous example, was this WW doesn't necessarily mean that there are two letters next to each other in the message that are the same letter. So we wouldn't be able to use the trick of thinking they're either OO or LL, or one of the other frequent two-letter words. So how do we break this? Yeah?
You can still use statistical analysis because the and the is there.
But how do we know where the is? Well, okay, actually hold that thought. Yeah, so one thing we can do, so we can actually look at this and run through the same steps that we just did for the Caeser cipher to try to look at the frequency analysis. So we could calculate this, calculate what we did previously to try to see which ones were most correlated with the keys. And so we do things like 0.55, this was that correlation value of 22 would get us something like LKLGSSAY. Actually has say in it, right, which maybe 10 gets us something like this, 4 gets us something like this, 2 gets us something like this. So these kind of correlation values, even though they're very high, almost as high as the one that actually encrypted the last message, it's not actually decrypting the message, right? Yeah.
We know the length of the key. Just break it up by thirds to see if there are any repeats.
Yes, so just a second. So one of the core problems here, when we're trying to analyze a cipher like this, is that we don't necessarily know the length of the key, right? We know, maybe we can do this analysis and try to determine that yes, it looks like this type of cipher, but let's say we know it's this type of cipher, we don't necessarily know the size of the key. So this is some terms that help here. So the period is the length of the key. So you think about like physics, like the period of a pendulum, right? Because the key is repeating over and over. I don't know where that comes from that, but it helps me. And the other thing that we just touched on is that the key is in each nth, based on the period of the ciphertext, was encrypted with the same key. So there are multiple alphabets if we think about. Whereas a Caeser cipher is monoalphabetic, right? It only has one alphabet. This cipher has multiple letters. So the general approach is exactly what was just said. So we want to first try to figure out the period of the key. Then when we can try to figure out and establish the period of the key, then we break the message up into n different parts. So if we take every nth letter and say these are all encrypted with the same Caeser cipher, and we can actually just use techniques that we just did in the Caeser cipher to try to decrypt this. But what's the difficulty here? If we just, let's say, do this kind of analysis we did here of looking at this correlation and then try to break it like this. Let me phrase it. So actually, I won't rephrase it. So we take every nth character. Let's say we've somehow determined that the ciphertext is length 3. We take every third character and say that's all with the same alphabet. We run some, and we know that it's all the same alphabet, so it should have the same statistical distribution as English, so we can shift it over. So what's the problem there? Or what's the difficulty with that approach? Yeah?
Sample is going to be a third the size of what it was.
Yeah, so one problem is going to be a sample size problem, right? With a very small message, the amount of letters that we have is only going to be a third, so the correlation may not be as high. What else? Yeah.
Won't know, even if you find out what the key is, you won't be able to recognize it because you can't determine a message by every third character. So you're going to have to use it in parallel with doing the same process on the other 3. And then you're going to have several combinations to go through, and you have to iterate a lot more before you get something that might make sense in English.
Exactly. So part of the problem here is that the second one that we tried in this previous example was the actual plain text. And we knew it because we knew that it was English when we saw it, right? But if you take the third letter of a message, that's not necessarily going to be the case, right? So you have, so kind of the interesting thing here is that these things are interlinked, right? These different alphabets, but it's not necessarily exactly the same way as the Caeser cipher. So we may have to like use kind of a weighted approach and try different combinations based on how likely we think they are. What else can we use? Yeah.
You have all three of them going at the same time, and then when you get the final message, compare its statistics to your goal statistics.
Yeah, definitely. So we could try to solve each problem independently, right? Come up with pops. Well, I think even if no, because they would have each individual alphabet, let's say, has the right distribution. If you bring them together and aggregate them, they should also have the correct distribution. You need some way to know that you were correct or not. Yeah.
So if you're doing it, like, so you know that if you know the size of the key, it's n.
Mm-hmm.
It means that you also have n sample sizes too.
Yes.
There'd be a smaller sample size in there, so that you just find this key the same letters in the same positions. But then if you
Say that again. Same letters in the same positions.
yeah, like
Wow.
if you find like let's like you say an E in the second position, you find out how many the distribution of the an E in the second position, and then from there you can start trying to break it down that way. Again, so that's a Caesar. That's like 3 different Caesar ciphers at the same time.
Right, right. But the difference is when we wrote the Caesar cipher, we knew because the message appeared. Right? Taking the third letter of the message, we won't necessarily know when we've actually broken that specific alphabet.
Well, what we're going for then is trying to figure out what the message of the key. Like you're trying to figure out, like, if you can figure out one part of the key, then you can start figuring out the other parts of the key.
How can you start figuring out the other parts of the key? All right, let's think about it. I'm gonna skip over that so we can look at it. So we're gonna use this ciphertext. So this is gonna be a ciphertext, it's a little bit longer. We probably try to run the same analysis. The spaces are just for our visual reference. They don't mean anything here. So how can we find the period of this message? Yes?
Brute force.
We could try brute forcing it, but then we'd have to have a good way to, like we said, verify whether messages are correct. I mean, we could definitely try it.
So you could do that with a dictionary. If you're going to automate it,
Mm-hmm.
if you were going to run all the combinations for all the periods and then do all the analysis and automate all of that, every time that you came up with a potential or a candidate decrypted plaintext cipher, you just run it against a dictionary to see if any of the groups of letters that are in there appear in an English word dictionary. And you might set a threshold that, I mean, we're going to expect that the majority of the plaintext is going to be all English, so your candidates would have to have at least 3 English words. You'd probably get a bunch of like
Random does or in or a. Yeah.
Eventually it would find it.
Yeah. That'd definitely be an approach we could take. So if we just wanted to brute force it, but let's go back to this guy. So we just look at this ciphertext. So we know. Okay, let's say we know. We know that the length of this key is 3. Right? But let's say we just have this ciphertext. How could we maybe try to determine that? Do you have an idea?
Well, in the previous example, the string letters E, O, O, the one we were doing before was open and force.
The Caesar? This one?
No,
Oh, I see this one.
that one, yeah. The string letters O, E, Q, 0, O, O, G appear twice in there.
probably longer. So why do you think that happened?
Because it's probably, it's probably a 6-letter word.
What is this OEQOOG?
Yeah. It's probably a word that got repeated and wound up in the same spot in the period.
So let's look at this one, right? So we know it's 3. So are there any? Let's use the same idea. Are there any repeats here? OPK.
Is in there twice.
OPKW. The W actually repeats as well, right?
Oh, yeah.
Yeah. So this is 4 letters of the ciphertext that repeat, but we know that the key is only 3. Why did this repeat?
My gut is telling me that it's purely coincidental. So you picked a bad message. You should have added an extra inconsequential word into your plain text to separate those 2 instances of the word the, so that it both get translated to OPK. And the same thing, even if he's right, you could have written a better message that expressed the same idea and encrypted it the same way, and not had that inherent weakness of those 4 consecutive characters getting repeated after a period.
But why are they repeated?
Because they coincidentally, the same plain text was getting encrypted with the same corresponding key values at the same location.
At that exact same location. So going back, right, looking at the plain text, we have THEB and THEB are all encrypted by VIGV, right? So it just happens that we have characters in our plain text that are repeated, which are likely to happen. I mean, with something like the, right, or in or a. I mean, this is definitely likely to happen in text. And it happens that our key overlaps, not necessarily the first character of our key, that doesn't matter, but the fact is the key repeats across here, THEB and THEB. So then, what does this tell us then about the period? Does this mean that the period should be, that the key length should be 4 because there's 4 characters that happen to be encrypted the same and repeated? The sequence, the OPKW, was repeated? Yeah.
You can just pick one letter that was encrypted by one part, like that you know it's the same, and then see how many letters are between the 2 of those.
Yeah, so I would think that the OPKW, right, and OPKW were likely encrypted by the same key letters. And I would say that, what's the difference here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the difference between those 9, so then what does that tell me about my key? Some factor of 9, right? It should be some factor of 9, which makes sense here because it's 3. So then this was actually and I believe for a while that the Vigenère Cipher was considered actually a pretty secure cipher. Kasky actually made this realization that repetitions of the ciphertext occur because the key is passing over the exact same characters in the message, right? Like we said, if they were offset at all, then the would not encrypt the same thing, but it can be the case that it happens. And so the difference here is 9, and so we would think that the key is some factor of 9, either 1, 3, or 9. We know it's not 1 because we can do a distribution analysis and realize we did that and realize it's not really any of those. We could try 9, but that would be kind of a long key. And so what we want to do, so we actually, that was really good noticing that. I don't know that I would notice something like this. But you would then see that, so what you'd want to do is try to find all repetitions in this text. And so we can do that, and we can find all the possible repetitions. And my OO, OEQ, OOG, calculate the start and end characters, get the distance, and get the factors among them. So how does this help you? Do you try all of these possible combinations?
Start with the most common. 2 is very common.
Start with the most common? So what's likely to happen based on probability? That 2 characters next to each other just randomly get to are the same? Yeah, you have a thought?
Well, I was just gonna say I would start with the longest one
Why?
because I mean 2 is gonna be a factor of every even number. So, well, sorry, I'm looking at the factors on the side that I would use to pick the length of my period, and I would start with the longest one because any of those small numbers are gonna occur way more frequently just because they're factors of a lot of numbers.
Right, so first thing we think about is the length of this repetition. You want to start with the longest one because that's least likely to occur just due to random chance, right? Because even if you're 100% randomly encrypting this message, you're likely to get some repeats just because of randomness. So you want to start there, and you'd say that, well, okay, all right, we'll stop here, but